Hello and welcome to video 2 in our series on learning basic electronics using Tinkercad circuit simulation. Today we're going to explore some fundamentals of electricity and get a closer look at series and parallel circuits. Developing an intuitive idea of what electricity is doing inside of a circuit or electrical device starts with a simple analogy and three key terms: voltage, current, and resistance. Electricity flows in a closed path from regions of higher potential energy to lower potential energy. That potential difference is called voltage, and we can think of it as pressure in a pipe system. The greater the pressure, the greater the voltage. Current is analogous to the flow rate of water in a pipe system, for example, gallons or liters per second, and is measured in amps. And finally, resistance, with symbol omega and units of ohms, is a measure of opposition to flow. For example, if a pipe was filled with small rocks or sand, water could still flow, albeit at a reduced rate. Voltage, current, and resistance are related mathematically by Ohm's law, an extremely simple yet powerful bit of math that we will use throughout all electronics projects. Power, measured in watts, is also related by simple math and will be helpful when wondering how much energy is being consumed by a given circuit element. In other words, how hot will it get? With Ohm's law, if we know any two parameters, we can calculate the other characteristics of a circuit. Let's take a look at the tools of the trade and see how we can measure values such as voltage, resistance, and current, as well as visualize how electrical signals change over time. There are four pieces of equipment that will commonly be used. A bench power supply is used to deliver power in the same way a battery or wall plug adapter would, and has the added bonus of being adjustable for both voltage and current. An oscilloscope lets us see how an electrical signal changes over time. It's worth pointing out that everything happens very fast in the world of electronics. Terms like kilohertz, megahertz, or thousands or millions of cycles per second are common. Oscilloscopes let us see what happens to electrical signals at these timescales. Function generators do the opposite of oscilloscopes. They produce time-varying electrical signals that are useful in testing. We'll use one here to demonstrate the difference between alternating current and direct current, AC or DC, as well as look at some signals in the DC range that are also time-varying or changing over time. Finally, we have the humble multimeter. In a vast majority of cases, a power supply and multimeter are all that are required to work with electronics in Arduino-based projects. The multimeter, as its name implies, is a multifunction sensor that can read voltage, current, or resistance based on the way it's connected to the circuit. Voltage and resistance are the easiest quantities to measure directly and work with. If the function generator is configured to output a DC square wave, that is, a signal that varies from 0 volts to 5 volts over each cycle, we can measure that voltage with the oscilloscope. A direct current is said to flow from positive potential to negative potential, or ground. Current only flows in one direction. An alternating current is one that is said to change directions once per cycle. The electricity that comes into our homes is 120 volts at 60 hertz. In other words, 60 times per second, the voltage changes from positive to negative and the direction of current is reversed. We won't worry about AC too much in Arduino projects or even most hobby projects. It's all DC. By convention, the positive terminal is denoted by red and the ground terminal is black. This color convention is used throughout electronics, so keep in mind that red will generally signify the positive side of a battery or power supply, and black will signify the ground terminal. Series electrical circuits are conceptually the easiest to understand and implement. Series, as the name implies, refers to the sequential connection of components between a start and end point. In this example, we have a 1.5 volt battery connected to 3 resistors. Resistors oppose the flow of electricity, and the degree to which they do so is stated in ohms. Here we have 3 1K ohm resistors connected in series. On the right, we have the same circuit, except this time there are multimeters connected to measure the voltage across a single resistor, as well as the total current flowing through all 3. Note the method in which each is connected. The multimeter measuring current is in series with the circuit, whereas the multimeter measuring voltage is in parallel, and we'll talk about parallel configurations in just a moment. Let's connect a multimeter to the circuit on the left and measure the resistance of one of the resistors. Just as in measuring voltage, the multimeter is connected in parallel with the component we want to measure. Unlike voltage, where the measurement is taken with the circuit powered, to get accurate resistance values, the circuit must be powered off. For resistors in series, the total resistance of the circuit is the sum of all resistors. Rearranging and applying Ohm's law, with a voltage of 1.5 and a total resistance of 3,000 ohms, we get a current of 0.0005 amps, or 500 microamps, and the multimeter connected to measure current confirms this. One important thing to keep in mind with working with Ohm's law are the scale of units surrounding each variable. For example, resistance is calculated in ohms, so a 1K resistor would be 1,000 ohms, a 100K resistor would be 100,000 ohms, and a 1 megohm resistor would be a million ohms. Current in most Arduino projects is given in milliamps or microamps, that is thousands or millionths of an amp. Ohm's law needs amps, so be sure to use the right number of decimal places when plugging numbers in. Parallel circuits are exemplified by components that are connected side by side with respect to a start and end point. The example series circuit is rearranged by connecting each of the 3 resistors to positive and the other ends to the ground terminal. As before, we have an identical circuit to the right with multimeters connected to measure voltage and current. What is immediately evident is that the total current through the circuit is greater than the series circuit, 4.5 milliamps as opposed to 500 microamps. The reason for this becomes clear when we attach a multimeter to measure the total resistance of the circuit. In a parallel configuration, the total resistance of all 3 resistors is the sum of the reciprocal resistance, or 1 over R. 3 over 1,000 simplifies to 333 ohms. Let's look at a practical example of series and parallel circuits. We would like to illuminate 3 LEDs using a 4.5 volt battery pack. If we connected each LED in series, we would find that the battery cannot provide enough voltage to turn on the LEDs. By connecting each LED in parallel, we trade voltage for current requirement. That is to say, the battery pack's 4.5 volts will be available to each parallel branch of the circuit. However, the total current consumed will cause the battery to drain quicker. This is a design trade-off that we have to make. In addition to a specified operating voltage, LEDs are sensitive devices, and if too much current flows through it, it can be destroyed. To mitigate this risk, we'll add a single resistor in series with the LED. This has the effect of limiting the current through each LED and is said to be a current limiting resistor. We'll see a lot of this type of circuit protection in Arduino circuits as we explore further on. By choosing the appropriate value for each current limiting resistor, we can operate LEDs at a maximum brightness level without the risk of burning them out. Now let's see how current limiting resistors can be applied to an example Arduino project. In many cases, we may want to have an indicator LED that signifies some event or condition in our project, or a method to get visual feedback when an event in our code takes place, or is absent. We'll start off with importing an Arduino Uno and connecting a red LED and current limiting resistor. We'll explore in later videos the multifunction nature of Arduino pins. For now, we'll use pin 10 on the digital side to serve as our positive terminal, and ground on the Arduino as our ground terminal. Just as LEDs are current-sensitive devices, the pins on the Arduino are only capable of delivering between 20 and 40 milliamps depending on the model. In the larger picture, it is more important to protect the Arduino pin from excessive current draw than it is to protect the LED from excessive current flow. So whatever value of resistor we choose, we want to make sure that the total current is less than 40 milliamps. This concludes our introductory look at basic electrical theory and series and parallel circuits. We'll draw upon this knowledge in future videos as we develop more complex circuits as we work towards our electronic dice circuit goal. As always, if you have any questions or would like further information, please visit us on the web.